Alright, today we're going to talk about the mean value theorem, concavity, and the second derivative test. So the mean value theorem is going to be very similar to Rolle's theorem. Concavity is going to be something we've seen but we haven't really talked about yet, and then the second derivative test is another way for us to find maximums and minimums, or to determine if something is a maximum or minimum, I should say. Okay, so the mean value theorem. So again, this is on your sheet of information, but here's a picture to go along with it. So if f is continuous on the closed interval a to b and differentiable on the open interval a to b, then the mean value theorem tells us there is a point c in a to b such that the derivative at c is the slope from a to b. So f of b minus f of a over b minus a, that's just a very fancy way of saying y2 minus y1 over x2 minus x1. So that's slope. So if this is a and this is b, and if I draw some line through them, so that's that line, then the mean value theorem tells me that there has to be some point c, let's say like, I don't know, right here, that the slope of the tangent line will have the same slope. So that's what the mean value theorem tells us. Again, that's basically an extension of Rolle's theorem. Rolle's theorem was specific about that the slope is going to be 0 at some point if a and b are the same, which is just a specific example of the mean value theorem. Also, one other thing I want to mention, because this comes up a lot in these theorems, they're very specific about closed intervals and open intervals. And so, well, why is it continuous on the closed interval but differentiable on the open interval? Well, remember, if this is an endpoint right here, or this is an endpoint right here, it can't be differentiable at that endpoint even if the endpoint exists, and that has to do with our definition of differentiable. So if you look back in your notes at differentiable, that's why it has to be differentiable on the open interval but continuous on the closed interval. Okay, so I want you to do an example. Find all the values in C, or find all the values of C in the open interval a, b, such that f prime of c is f of b minus f of a over b minus a. So you're trying to find a value or values of c in this interval where that is true. So pause the video, unpause when you're ready to check your work. Okay, you should end up with in the interval 1/2 to 2, including 1/2 and 2, c is going to equal 1. So how do we come up with that if you're really confused? Well, first I found what is f of b. Well, f of b is f of 2. So I plugged in 2 to the function and I got 3/2. What is f of a? F of a is f of 1/2. So I plugged in 1/2 into the function and I got 3. So then I figured out what is f of b minus f of a over b minus a. So 3/2 minus 3 over 2 minus 1/2 is -1. So I'm trying to find a c value where the derivative equals -1. So then next I found the derivative. I used the quotient rule, but you could also split up the fraction and do each part individually. Either way, you should end up with f prime of x is -1 over x squared. So now I'm trying to see at what x value does -1 over x squared equal -1. So if I solve this equation, multiply both sides by x squared, divide both sides by -1, I get x squared equals 1, so x equals plus or minus 1. But -1 is not within my interval. So the only answer is going to be x equals 1. Had both of these not been within my interval, then there would be no value within that interval. But that couldn't be true because of the mean value theorem. So then we end up with c equals 1. Alright, so now we're going to go through some definitions. So definition of concavity. So if f is differentiable on an open interval I, the graph of f is concave up on I if the first derivative is increasing on the interval, and concave down on I if the first derivative is decreasing on the interval. So here we can see a picture of what concave up means and what concave down is indicating. And so that's what we're talking about when we talk about concavity. So let's think about this. If f prime is increasing, what has to be true about f double prime? And if f prime is, this should say decreasing, what has to be true about f double prime? Okay, so there I changed it to decreasing. So now I want you to pause the video and think about that for a second, and unpause it when you think you know your answer. Think about the relationship between f prime and f double prime. Alright, so if f prime is increasing, then the second derivative has to be positive. And think about what that means, because the second derivative is actually the first derivative of the first derivative. And we know the relationship between a function and its first derivative is that if the function is increasing, then the derivative is positive. If the function is decreasing, then the derivative is negative. So that should hopefully make sense that if the second derivative is positive, then the first derivative is increasing. If the second derivative is negative, the first derivative is decreasing. Alright, so again, this is just a theorem on your sheet, but I want to go over it. So let f be a function, so this is the test for concavity. Let f be a function whose second derivative exists on an open interval I if f double prime of x is greater than 0 for all I in the interval, or for all x in the interval I, then the graph of f is concave up in I. If the second derivative is negative in the interval, then the graph is concave down in I. So this is almost the same thing as what we did for our first derivative test, but now we could use the second derivative to test for concavity in the same sort of fashion. Point of inflection. So the definition is let f be a function that is continuous on an open interval and let c be a point in the interval. If the graph of f has a tangent line at this point, c f of c, then this point is a point of inflection of the graph of f if the concavity of f changes from upward to downward or downward to upward at that point. So here are a couple pictures of changes in concavity. So here we go from concave up to concave down. Here we go from concave down to concave up. Here we go from concave up to concave down. So the concavity of f changes at a point of inflection. Note that a graph crosses its tangent line at a point of inflection also. One thing to point out, so remember that the tangent lines, the slope of the tangent line comes from the derivative, but the actual derivative is not the line. So keep that in mind. These pictures here, the lines, the derivative is just the slope. Okay. Points of inflection. So here's our definition. If c, f of c, is a point of inflection of the graph of f, then either f double prime of c is 0 or f double prime does not exist at x equals c. So again, our test for inflection points is going to be the same as our test for critical values, or the way we find them is going to be the same way we find critical values with the first derivative, where we're looking for where is the derivative 0 and where does the derivative not exist. But now we're talking about the second derivative. So properties of graphs. Well, a lot of this we've talked about already, but let's just kind of sum it up. So this point here would be a relative max. This point down here would be a relative min. Right about here would be an inflection point. And over this interval, we're concave down, and over this interval, we're concave up. And we don't know if these are open or closed points here, so I can't say whether those are maximums or minimums based on the information given for this problem. Okay, so now let's do. Okay, so what if we want to find inflection points? Well, we're going to follow a similar process to finding minimums and maximums. We're going to use the second derivative though. So we'll go through this one together. If f of x is 2x cubed minus 3x squared minus 1, then the first derivative is going to be 6x squared minus 6x. And then the second derivative is going to be 12x minus 6. So now remember that inflection points exist, or possibly exist, at values where the second derivative either equals 0 or does not exist. Well, since this is a polynomial, there's no place that it does not exist, but if we set it equal to 0, I would add 6, divide by 12. So my possible points of inflection are at x equals 1/2. So now I'm going to set up a chart just like I do for my first derivative test. I'm going to use 1/2, and then I'm going to pick values to the left of that. So I'm going to say 0, and to the right of that, so I'm going to say 1. And I'm going to test if those are positive or negative in the second derivative. So f double prime of 0 is negative 6, so that's negative. And f double prime of 1 is positive 6, so that's positive. So I can see that here it was concave down, here it is concave up. So now, just like with the first derivative test, we need to verify this using words and symbols. So f double prime of x is less than 0 on negative infinity to 1/2, and f double prime of x is greater than 0 on 1/2 to infinity the point 1/2 negative 3/2 is an inflection point. The negative 3/2 came from figuring out what is f of 1/2, 2 times 1/2 cubed minus 3 times 1/2 squared minus 1, or negative 3/2. And so that's our test for inflection points. So it's basically the same as our test for maximums and minimums, except for now we're using the second derivative. Alright, so in general we want to remember if the second derivative is positive, it's concave up, and if it's negative, it's concave down. Here's a lovely picture showing that positive is happy, negative is sad. Sometimes I'm sad. Sorry, I digress. Alright. So I want you to do this example. So I want you to find the inflection point. So pause the video, unpause when you're ready to check your work. Alright, so you should end up with 2 points of inflection here, negative root 3 over 3, comma 3/2, and root 3 over 3, comma 3/2. So how do we get those? Well, this one was a little bit more work for the second derivative. First derivative wasn't too bad. So first I rewrote the function as 2 times the quantity x squared plus 1 to the negative 1. Now I just did the chain rule for the first derivative, so I bring down the negative 1 and take the derivative of the inside. So I get negative 4x times the quantity x squared plus 1 to the negative 2. Now I had to use the product rule. So when we use the product rule and simplify, it's a little bit more work. So the first one is the derivative of the first times the second plus the first times the derivative of the second, and when I do the derivative of the second I have to do the chain rule again. So then I simplified and I have 2 terms, negative 4 over x squared plus 1 squared and 16x squared over x squared plus 1 cubed. So I got a common denominator by multiplying the top and the bottom of the first term by x squared plus 1. Once I do that and simplify, I end up with a second derivative of 4 times the quantity 3x squared minus 1 over x squared plus 1 quantity cubed. Set the numerator and denominator equal to 0 to find where the derivative equals 0 and where the derivative does not exist. I only get 2 possible points of inflection, 1 over root 3 and negative 1 over root 3. Notice that I don't rationalize them until the end because sometimes it's nicer to work in this fashion. I do my second derivative test, plug in values, and then write my answers using derivative speak. I'm going to stop this video here, go to part